All right, welcome to another session of DGX Compare. Today we're going to be working with NVIDIA's Nemotron 3 Super 120B model. And essentially it's a 120 billion parameter model, but this version is quantized down to around 12 billion by using NVIDIA's FP4, which is the floating point 4 quantization model, protocol. One thing special about the Nemotron models is that it's designed and worked on by NVIDIA specifically for Spark or DGX systems, and in this case, the Spark. So it's actually highly optimized to work with the tensor infrastructure that's inside of these devices. I made another video some time ago with this 120 model, except it was running on a single DGX device, that one right there, which is the Acer GN100. But today we're going to be testing the exact same flow, but this time using a cluster. So here we have a DGX Spark clustered together with the Acer GN100. They're exactly the same platform, it's just different cases. And they're connected via NC7 connectors right there. And I preloaded the models, and here's something that's really cool. So whenever you try to install this 120 billion parameter model, at least in the previous time we did it, that system memory is like 120 already, even before. And this is just loading up the weights. So with zero memory, that's already like that. When you start using it more and more and more, I used it for a couple of days, maybe 10 queries. It started struggling, and then it eventually crashed. And so that's why I wanted to try to model out with the cluster. So we've gone ahead and set up all the watcher tools. We're going to be watching all the cores. We're going to watch the swap. We're going to watch the GPU utilization. This is the what's called the lead node, and that's the worker node. So a little bit about clustering for those who don't know. So the way this is clustered, it's called pipeline parallelism. Tensor parallelism is when you have a single, single box that has multiple GPUs in it. Like let's say you're sitting on a cloud on an A100 or a B200. In this case, we don't have that because each of these systems only have one GPU. So we're doing what's called pipeline parallelism, which is essentially the same thing. Or maybe I'm simplifying that, but essentially it's two GPUs separately. And the way it works is that it's pulling the memory together. So each of these devices has 128 gigabytes of VRAM. And because they're connected together and clustered, they're actually sharing the RAM together. So instead of 128, it's now 256, right? There's some performance degradation with the memory because initially it's not that fast already. It's, I think, 273 is the spec on it, and it's probably down simply because you're connecting memory through a cable, right? So it drops it down to, I think, 213. And just for comparison's sake, Max, the same model on the Mac at 256 is running at 800, so 3 or 4 times the speed. But there are differences, right? The speed is fast in terms of inference, but it's only on the decode side. So for those who don't know, inference is 2 components. The first component is the prefill. That's when you actually ask it a question, and it's grabbing your question and doing all the research. And then when it grabs all that research, when it spits it out, that's called the decode phase. So memory bandwidth is important on the decode phase, and what's more important on the prefill phase is the infrastructure in which the model is gathering data. And in this case, this specific Nemotron model is designed specifically to be used on DGX systems. I mean, it is an NVIDIA product, and they designed it to work on the cloud versions of the DGX. And I think they've actually they're trying to showcase it for the upcoming DGX station. That's the $100,000, 768 gigabyte or 748 gigabyte memory kind of workstation that's coming out. And that's really, I'm looking forward to playing with that one day. But this is the kind of a small brother, so to speak, or small cousin of it. But we're still pretty powerful at 256 gigs of RAM. All right, let's get to it. So the typical query that we're using, tell me all about Tyrannosaurus Rex. And I'm misspelling Tyrannosaurus on purpose. And let's see the runs. All right, there we go. As I said, right, the prefill is really fast on these devices. I don't know if you guys can see, but this bottom one is the lead node. That's the Spark. If you take a look at the GPU utilization, it's only at 54%. System memory is stable at about 100. But look over here on the GN100, which is the worker node, it's already at 92%. So this is doing all the heavy lifting. If you take a look at the CPU usage over there, look at all the cores. You have, I think, CPU 18 over there, CPU 8 over there. They're all at almost 100%. And look at it, all the different colors there, all over the place. But if you look down here, it's also all over the place, right? Because the cores are getting hit, but not as heavily as it's being done over on that side. Again, when you're talking about pipeline parallelism, it's three components, right? So you have the orchestrator, which establishes the connection between the two physical GPUs and the devices. In this case, we use Ray. That's RAY. And Ray is an orchestrator tool. It's kind of like, think of it as like it's a cluster landlord, right? And what it does is it acts as a resource allocator. So let's say you request a pipeline stage across the two different platforms. Ray will decide which machines, which nodes to use, determine which GPUs are there and whether or not we can allocate the work there. And then when it decides that, it hands over all that information to what's called NICL, that's NCCL. NCCL is NVIDIA's pretty much memory management system. And what it does is it allocates percentages of the tasks in between the two GPUs. They have what's called escapes me. What do you call it? There's a term for it in large language models where they group the work together for the nodes, and essentially they're called layers. There we go, layers. So you have like 32 layers, for example, and the first 16 layers, exactly half is being done, is being allocated by NICL, right, the NCCL system, to the first node, and then the next 16 layers to the second node. And the actual allocation of when that happens and when it actually gets sent over is a little bit out of my scope right now. I'll do more research on that. But either way, Ray does the orchestration, NCCL does the actual memory management and layer management. And in the end, the end user just really sees the tokens. Okay, so how are the tokens looking like? I'd say this is 15, maybe 15. I think the last time when we ran this on a single device, it was like 5. It's like, as a large metabolism apex predator like that was the speed of it, and it's really unusable. This I can live with. Let's take a look over here. Memory is still stable, consistent at 108. We're not even at red yet, right? Remember, there's 128 available. It's only using 108. So let's say, I don't know, 90%. So you still got 10% there. Same thing over here. So you have that small buffer, right? But the GPU utilization on the GN100 is much higher. It's double. It's a 90% over there, and here it's only 50, 60%. If you look at the CPU, the cores, oh, they're all over the place there, and all over the place here too. But look, consistently, it's a straight line there. Whereas here, it's jumping up and down. So that's probably NICL doing that management. Let's feel the devices. Can't really hear anything. See, it's the GN is cooler for whatever reason. I was expecting that this would be a lot warmer because it's doing all the work. Remember, power usage is not from memory. Power usage is from GPU utilization. So the more the GPU is being worked, the more the hotter it gets, and so the fans will start turning on. All right, looks like it's completed already over here. That's done. I think there's always something in the end that it kind of look over here, it's actually still spinning. I think what's happening here is after the decode's completed, what it actually tries to do is now add everything that it's learned into KV cache. That's the key value cache that it stores as part of a conversation, so that, you know, if you ask it a question about a certain, you know, statement that it said over here, it knows that it said it and it knows the context, right? And I think that's the part here where it's working a little bit more. Again, it's just it's not really doing anything that you can see, but the GPU utilization is high over there at 90%, 54% over here, and it's still spinning, right? Let's see if we can actually do something to trigger that. I'll say, oh, there we go. See? So it completed. It said, oh, there could be some follow-up, but it's still spinning. It's still doing something. I think at some point it's going to have to end. I've seen it before. I think something shows up there. But anyways, I mostly wanted to show what pipeline parallelism looks like when you have a cluster. And I think we've pretty much shown that here in what happens with the cores on the main node compared to the cores on the worker node. The GPU utilization on the worker node versus the GPU utilization on the main node. Oh, look. I don't know if that was there before. I'm going to look at the video. I don't know if it had the actual icon or a picture of a Tyrannosaurus. But I'm kind of hoping this thing shuts down before this video gets too long, because what I want to show you guys is after it finally ends, or, you know, all the work is done, the utilization will actually drop down to like 5%. Really just sitting there waiting. Anyways, I'm going to look for and paste the link to the other video, which is when we were running this exact same model on a single Spark or a single DGX system. And that was actually pretty important as well, because not a lot of hardware will allow for you to even load this model into memory and not crash it. So there's such a thing as loading up a model into memory, but it being unusable when your token speed is like 5 or when it starts crashing. That's different than when you can actually load it up into memory and still be usable. So I think this is why I prefer using big models or large models that are designed specifically for a framework. And in this case, Nemotron is that specific tool. All right, so Nemotron 3 Super 120, NV compressed and quantized down to 12 billion through 4-bit quantization.